Welcome all. This is a TCS seminar at Carleton University. So for this week, our group have two guests, Vida Dujmović and Pat Morin from Ottawa. You're from Carleton University. Vida is from University of Ottawa. And today we will see a talk about labelings, about adjacency labelings. So it's great to have you both here. The floor is yours.
Thank you. So thanks for having me for a visit. I've given talks a couple of times before in this series, but never actually on site. So it's nice to give a real talk. So thanks for the opportunity to do that. So I'll be talking mostly about this recent work with these authors, Vida, Cyril, Gwenaël, Piotr, and David Wood. And it's about adjacency labeling in minor closed graph classes. And so then the first question is the first phrase on the slide, adjacency labeling. What is this adjacency labeling? And most authors will say this is a really old problem. It goes back to 1988. People have been studying it. I think it goes back further than that. And let me explain why. So here's a friend of mine. His name is Joachim Gudmundsson. So if you think back thousands of years, 2,000 years, if you imagine Joachim lived in a small village. In that small village, there's probably only one person named Joachim. So his first name is sufficient to identify him. So the question is, what's the point of his second name? Why does he need a second name? Well, if you meet someone else in that village named Gudmund Jakobsen, you might start to put things together and realize, oh, maybe this point of Joachim's second name is to express a relationship between himself and Gudmund. And the natural thing to assume would be that maybe Gudmund is Joachim's father. And if you walk around the village some more, you'll run into these other people, and you'll put together the fact that, oh, I actually know who everyone's father is in this town now, just based on their names. Okay? And so take a step back for a second. Once I know what the protocol is here, once I realize this is how their names are set, then if you give me the names of any two people, I can immediately tell you whether one is the father of the other, just from their names. So here I would deduce that Gudmund is the father of Joachim. Here I would deduce that Gunnar and X-12 are not parents of each other. And in fact, I looked this up, and some references say that this is called patronyms, taking a last name, which is your father's first name. It's the oldest naming system in human history. Okay, so I think it goes back a little bit before 1988. But let's bring it into the modern version of adjacency labeling, what this is about. So there's a few definitions, and you have to be careful exactly what order you present them, otherwise you make a trivial problem, as you'll see here. But there's a few things that come into it. So one is just a function A called an adjacency tester. It takes 2 bit strings as input, and it outputs a 0 or a 1. That's the only restriction on A, what its inputs and what its output looks like. And now, if you give me a graph and a labeling of its vertices with binary strings, that's just called a labeling of the graph. And now you have to look at the relationship between these two things, and you'll say that that labeling is an adjacency labeling of that graph for this adjacency tester if this condition is satisfied for every pair of vertices. So you look at the labels of any two vertices in the graph. If the adjacency tester A outputs 1, then you know that the edge between those vertices is present in the graph. If it outputs 0, then you know that the edge is not present in the graph. Okay, so that's what it means for labeling, well, to be an adjacency labeling of G for A. And if you just think about one graph, then this is a kind of a trivial thing because there's no restrictions on this function A. So you put any labels you want on the vertices, and it doesn't matter as long as, let's say, they're all unique. Then the adjacency relation just gets encoded in the function A. So for one graph, it's not an interesting problem, but if you claim that this labeling works for A, then you know what A does to all of these 3-bit inputs. Here it would output a 1 because those two vertices are adjacent. There it would have to output a 0 because they're not. But it gets interesting or non-trivial when you talk about a whole class of graphs. And there you say that a class of graphs has a f of n-bit adjacency labeling scheme if there exists one A, one tester. So just like when we talked about what we did with people's names earlier, there's just one way to deal with that. It doesn't matter what village of people you're looking at, it's always done the same way. And what you need is that for every n-vertex graph in your class, and for every n, it should be possible to label the vertices of that graph with bit strings of length f of n, so that this is a real adjacency labeling of that graph for A. Okay, so A is fixed for all graphs in the class, and you have to be able to label the vertices of every graph in the class so that A gives the correct answer for every pair of vertices in that graph. Okay, and just back to the village view of things. What does this mean? Well, most of the time, this means that every person in the village has to have a unique name, different from everyone else's. And the names should be chosen so that this algorithm A, which tells you whether one is the father of the other, works for that group of people in that village. But if you go to a different village, which is like a different graph in the class, there can be people in that second village which have the same names as people in the first village. That's allowed. Okay. Good. So here's a really simple example. If you consider the class of hypercubes, that's the class G you're going to start with. Here's an adjacency tester, which takes 2 bit strings x and y, and it outputs 1 if the difference between those bit strings is exactly 1 bit, so they differ in exactly 1 location. That's the adjacency tester. And actually, from the definition, or one of the definitions of the hypercube, you realize that this is going to work because one of the definitions of the hypercube is the vertices are bit strings of length d, and 2 vertices are adjacent if they differ in exactly one bit. So class of hypercubes has a log n bit adjacency labeling scheme. Okay. Clear? Please stop me at any time if there's any questions. Okay, and this is all very computer science-y, bits and labels and measuring, counting things in bit lengths. If you don't like that, there's another view of all of this, which is about so-called universal graphs. So if a graph class has one of these f of n bit labeling schemes, there's qualifiers that it should be injective in a graph. Every vertex should get a different name. Then that means that for every n, there is a graph un, which is universal for that class in the following sense. For every n-vertex graph in this class, that graph appears as an induced subgraph of this universal graph. And the size of un is exponential in 2 to the f of n. And the proof is kind of trivial. The vertices of the universal graph are the bit strings of length f of n, and there's an edge present if the adjacency tester tells you the edge should be present. That's how you define it. Okay, and that's all I will say about this. We'll talk about, we'll really talk about adjacency labeling for the rest of this. I just will point out, though, that this is an example where I think the computer science adjacency labeling perspective is much more useful than this problem here, because I would have no idea how to approach this problem if it was stated this way. Okay, so I promised, I think, in my abstract that I would give a summary of previous work. So here it goes. So in modern times, but actually before modern times, people studied this for trees. And one solution for trees, which people came up with about 2,200 years ago, is that every vertex gets a unique identifier, and it gets the name of its parent as well. So that is 2 integers, each of size n, so that takes 2 log n bits, and from that you can tell if 2 vertices are adjacent in the tree. This got picked up again in, let's say, 1990 by Fan Chung, who gave a labeling scheme in which the labels have length log n plus log n plus a constant. The interpretation for universal graphs is you get a universal graph of size n log n out of that. And I mean, this log n is somehow, for me, the exciting part. That's kind of necessary. And then there's these lower order terms, but actually even the lower order terms got pushed all the way down to log n plus an additional constant, which means there is a tree of size order n, which contains every tree as of an n vertices as an induced subgraph. Okay, well, once you've solved the problem for trees, the next thing to do is to work with bounded tree width graphs. It's kind of the next step in complexity beyond trees. And for that, Gavoille and Gwenaël gave a solution in 2007, which uses log n plus little o of log n bits. And the little o of log n is something like the tree width times log n. But for the rest of this talk, this is the level of detail that I will usually go to on the smaller order term, just that it's little o of log n. And this is actually a really important result. It comes up, it appears again in various solutions to subproblems and everything else. Okay, once you do bounded tree width graphs, next question is about planar graphs. And planar graphs have a fairly long history of pushing down the constant here, which started with 6 log n in Muller's PhD thesis, but simultaneously in this Stock or Fox paper by Kanan, Mayor, and Rudich, which had a 4 log n. Somebody noticed, actually, a 3 log n is already easy from known results. Then the next big, yeah.
This is Schneider-Woods, right? That's 3 log n.
The 3 log n is Schneider-Woods, arboricity. Then down to 2. This is the Gavoille-Gwenaël. The fact that it's true for bounded tree width graphs gives you a 2. I'll explain that in a minute. And then the next big breakthrough below 2 here was 4/3 log n in 2020, and then finally log n in 2021. And here's the same slide again, but instead of references, it's the techniques that were used for these things. So the 6 log n comes from 5 degeneracy, because you can, orient the edges of the graph in such a way that each vertex has out degree 5, and then you play exactly the same game where each vertex gets a unique identifier and the list of up to 5 outgoing neighbors. So it's just a generalization of what you do for trees. So you get that from 5 degeneracy, but also if you have a 3 orientation of your graph, out degree 3 orientation, you get 4. And someone noticed a bit after that actually we already know that planar graphs can be decomposed into, the edges of the planar graphs can be decomposed into 3 trees, and we have solutions for trees. So let's just give a vertex of three labels, 1 in each tree. That gives 3. This comes from a 2 outer planar decomposition plus the bounded tree width solution. And then these last 2 come from product structure. It's a sort of recent discovery about planar graphs, certain structure that planar graphs have. I'll talk very briefly about it. I would say that this one here, it happened, you know, a month or 2 maybe after the discovery, but actually I think it was happening already like minutes after product structure was discovered, literally. And then this took a bit more work. Okay, so I want to talk about this 2 log n solution. And I'll give you the easy solution, and then I'll give you the harder solution for some reason. So you have a planar graph, and you would like to do this adjacency labeling with 2 labels of length 2 log n. What you know is that if you have a bounded tree width graph, then you can do adjacency labeling with labels of length log n. So you first consider the layer, so do a BFS layering of your graph. That's what this is from your favorite vertex. If your graph is not connected, you can do several layerings, 1 for each component. Do a BFS layering, and then consider pairs of layers, like 1 and 2, 3 and 4, 4 and 5, and so on. So if you just consider the graphs whose edges live inside each of those pairs, then, well, for 2 layers, this graph has small tree width. And, well, once you take a bunch of those and put them together, those are just disconnected graphs, each of which has small tree width, which happens to also have small tree width. So I can do adjacency labeling in this graph with log n bit labels. If I shift by 1, I can do adjacency labeling in this graph with log n bit labels. And every edge of my graph is either in the first graph or the second graph, or even both of them. So the way it works, what you do is you take a labeling in the first graph for your vertex, label in the second graph for your vertex, and then the adjacency tester is just, well, check if they're adjacent in the first graph or if they're adjacent in the second graph. That's the whole thing. Okay. Questions? Good. So hopefully that means everything is clear, not that you're completely lost. All right, here comes a harder solution that is useful because it illustrates something that is hidden by the previous solution. And the thing that's hidden by the previous solution is it's not exactly immediate that if you can do adjacency labeling, for instance, for each of these components, that you somehow for free get then an adjacency labeling for the whole graph. That's not actually immediate if you just think about the definitions. There's a little bit to do, and I'd like to explain what that little bit is that there is to do, because we have to do it a lot later. So same story, you take the BFS layering, and you take a labeling of individual blocks of size 2. Graph layer I, union layer I plus 1, and you do that for each I. So these blocks overlap. And if you think about a vertex of your graph, well, it will appear in 2 of these blocks. It will appear in the graph for layer I minus 1. So if the vertex is in layer I, it will appear in the graph for layer I minus 1, and it'll appear in the graph for layer I. Okay, so you give that vertex its 2 labels and an integer which tells you which layer it's in. So it's a 3-part label. If you look at the length of the label now, well, I have to encode the value of I, which is h, somewhere between 1 and h, so that takes about log h bits. I have to encode the label in graph I, the label in graph I minus 1. I don't know what those are. Those have at most n vertices each. So you can upper bound this certainly by 3 log n. And adjacency testing is easy if I give you the labels of 2 vertices, v and w. V is in layer I, W is in layer J. Then if they're in the same layer, I can just, this GI is the same as GJ, so these are both labels in the same graph. I use the adjacency tester on that. If I minus 1 equals J, then I have this as part of the label for V. I use it with that. And if I equals J minus 1, similar thing. And if none of that is true, that means I and J differ by more than 1, then they're definitely not adjacent because edges are always between consecutive BFS layers or the same BFS layer. Okay, good, but it looks like this is not only more complicated, but it's worse because you use 3 log n bits. But actually, you can save those, as I'll explain. So let's say Ni is the size of the graph Gi, the number of vertices in that graph. If you add up all of those Ni's, well, each vertex appears in at most 2 of those graphs, so you get something that's less than 2n. So that means if I look at the label of some vertex v in the graph vi, that's going to be something like log ni plus little o of log n. And now the other part of this label, which seemed a bit strange and didn't somehow appear in the other solution, was the row number, the value of I, where this vertex appears. Rather than encode that value as just the binary representation of I can use a variable length code, which encodes these integers 1 through h, each as a binary string, but they're not all the same length. It's sort of an ancient result in encoding theory that this should be a 2n, that I can do this using log of this sum, which is 2n, divided by the value of I, this particular, think of that as a weight for I. And the way logarithms work, of course, is that's just log n minus log ni. So now, if you look at the total length of a label, there's the value of the vertex I, the I that this vertex belongs to. Then there's the label of that vertex in that graph. And there's a cancellation that happens because this one has length log n minus log ni. This one has length log ni. So somehow those disappear and they only add up to log n together. Of course, you're still stuck with the second label here. So you recover the 2 log n, and it seems more complicated, but the point that I wanted to make is this trick of using a variable length code, sometimes called a weighted code or a biased code, to somehow get 2 labels to sum up to some total weight.
So isn't there a decoding issue? Because you now see a string of bits and you need to capture where the length of this variable length index ends.
Okay, so there's actually 2 decoding issues. That's a good one. So I'll ignore them here, except to say that, remember, we're talking at the level of detail of little o of log n here. And there's a standard trick for encoding integers, any integer, which is using a number of bits, which is logarithmic in the value of the integer you're encoding. This is an old trick due to Elias. And so when I say the label is the concatenation of 3 things, it's actually slightly more complicated. It would be something like, there is an integer which tells the number of bits in the first thing, That's at most log n, so that only takes log n bits to describe that thing. And then followed by the first thing, then an integer that tells you the number of bits in the second thing, followed by the second thing, then an integer that tells you the number of bits in the third thing, followed by the third thing. And that all gets covered. I mean, those extra bookkeeping bits just appear as lower order terms. In fact, log n terms. Yeah.
In order for these encodings of the levels to be useful, you also need to know which two of them are consecutive.
That was the other thing. And there is this little detail that you have to be able to know if I plus 1 equals j and if j plus 1 equals I. And I will leave that as an exercise to the reader, or listener in this case, using the fact, as a hint, I will tell you that actually these code words are just paths in a binary tree. And if if you look at the code word for I and the code word for I minus 1, there's a very simple difference between those two things. So if I give you the code word for I, there's a very short description of how you can get the code word for I minus 1. Erase something and then add something. So there's a little bit hiding there, both in the encoding of multi-part labels and this little thing. Okay. All right. So now we finally get to actually the topic of the seminar today. So this is supposed to be about H minor free graphs. So I should maybe say what a few of these things are. Before I talk about H minor free, let me tell you what an apex graph is. That is just a graph from which I can remove a vertex and the graph is planar. So the most famous example of an apex graph is the complete graph on 5 vertices. K5 is famously not a planar graph. If I remove one vertex, I have a complete graph on 4 vertices, which is almost as famously a planar graph. So K5 is an apex graph. Okay, so that's apex graph. Minor, so graph H is a minor of G. If I can delete vertices and edges from G, and then contract edges in G, and what I finish with is the graph H. So it's somehow hiding inside of G. And one thing you may realize really quickly then is, well, planar graphs, they don't contain K5 as a minor. So there is an apex graph that planar graphs don't contain as a minor. All right, so here's some results, but they all come from product structure. So apex minor free graphs were considered in this original paper recent 2021 paper that did planar graphs. In fact, what they proved in that paper is that every graph which has this so-called product structure has an efficient adjacency labeling, log n plus little o of log n bits. And a previous paper showed that apex minor free graphs, those which exclude some apex graph as a minor, have product structure. So that comes from the combination of those two things. And in particular, that implies planar graphs because there is an apex graph, K5, that doesn't appear as a minor in planar graphs. So the planar graphs are just a really special case of this. But there's also a bunch of other sort of classes of graphs which have this product structure. K-planar graphs, map graphs, H-frame graphs, K-matching planar. This is not an exhaustive list, but as soon as you get that these graphs have product structure, you immediately get that they have this log n plus little o of log n bit adjacency labeling schemes. But immediately, as soon as you leave this, and in fact it breaks really fast, if you take K6 as the graph you exclude, it's not an apex graph because if I remove any vertex, I still have a K5, which is not planar. The best known solution was still 2 log n, and that comes back from this this result of Gavoille and Labarelle, and a more complicated result about minor free graphs, which says that they can have their edges decomposed into two graphs of constant tree width. So I showed you how that works for planar graphs. It's this BFS layering trick. It's more complicated for minor free graphs, but it's also true. So exactly the same solution works there, and that was the best solution since up until recently. And so what I will sketch for the rest of this talk is H minor free graphs for arbitrary graph H, a log n plus little o of log n bit adjacency labeling scheme. And it only tangentially uses product structure. It sort of only uses what was known previously. But there's a lot of other things to pile on top of that. Okay. Questions? All right. So here's some of the techniques that are used. Well, we're going to use tree decompositions. And the tree decompositions we're going to use come from the graph minor structure theorem of Robertson and Seymour. Those apply to H minor free graphs for any H. Don't worry if you've seen recent talks about the graph minor structure theorem. We won't even look at the details of it at all. The thing you need to know is it tells you that if you have a H minor free graph, it has a tree decomposition whose bags are nicely behaved. And nicely behaved has, a complicated description. For our purposes, you can think of it as if I look at the graph induced by the vertices in a bag, it has a log n bit adjacency labeling scheme. In fact, a generalization of that. That's nothing new. That already came from what we knew about, from the product structured graphs. These graphs are not product structured, but they're close enough. There's a few exceptions, meaning you just take away a small number of vertices and suddenly you have product structure. And for adjacency labeling, you can imagine that if there's only a constant number of vertices which are somehow special, you can just deal with them in some brute force way. Okay, but this is a tree decomposition that you get from this. And so I won't give you the definition of tree decomposition, except to point out a couple of things. So it's sort of covers the vertices of your graph with bags. And, it has this property that if two vertices are adjacent, there must be some bag that contains them together. But the key point is that, and in the case of Roberts and Seymour, if you look at two adjacent bags, like these two, they have a small number of vertices in common. Some constant that depends only on H. They have only a small number of vertices in common. Okay. So here's where you start to see an immediate problem. If those two bags had no vertices in common, life would be much better for us. But that's not the case. For instance, if you look at this decomposition here, I have these vertices that show up here in the root bag. They also show up here. They also show up here. They also show up here. And they also show up here. Some of them show up in those places. And there's other vertices that are only in this bag, which could be adjacent to any of those vertices. Same thing along any of the bags along this path. And solutions in which you say, oh, well, give a graph more than one label, or give a vertex more than one label, they are not going to give you log n bit solutions. And in fact, we saw one such solution that leads to a 2 log n bit solution, but that was just because the vertices somehow only appeared in two graphs. Here it would be much worse. If I want to give a vertex label for this vertex in this graph, and in this graph, and in this graph, and in that graph, there's not really any bound on the length of the label in that case. Okay, so that's something we have to deal with. And the way we're going to deal with this is to introduce a generalization of adjacency labeling called mixed labeling schemes, which it's a complicated definition, which I'm hoping to convince you is worth sort of getting through from this picture, that not only assigns labels to vertices, but it assigns labels to cliques, and then does even something else to the vertices of these cliques, assigns really short labels that are specific to that clique. So that's the sort of trick we're going to use to deal with the fact that these vertices appear in many places. But that trick alone is not enough. Kind of looks like it is at the beginning, but then you realize there's an issue. So we have to do something a little more. We have to do a part, the Robertson-Seymour tree decomposition is just some tree. So we actually break it up into so-called skinny pieces, which don't have too many, which only have a small number of vertices in each layer, or bags in each layer. And if you look at what happens if you were to contract these skinny pieces, what you get is a tree of small height. And so that means we need a solution for skinny tree decompositions, for mixed labeling, and we need a solution for short tree decompositions, trees of small height. So those are the steps, and I'll try and explain them in moderate level of detail, let's say. Okay. Questions yet? Great. Okay, one thing to look out for, if you study tree width and graphs of small tree width, you don't think of this so much, but when you talk about a tree decomposition where the bags are not necessarily small, but they're just well behaved in some sense, but may have a lot of vertices, then you actually have to think always about two different kinds of graphs, and which one is the nice one and which one is the not so nice one. So for any bag, there's a set of vertices in there. If you look at your graph, those vertices induce a subgraph, just whatever edges happen to have both endpoints in that set. That's the induced graph for that bag. But if you look at the fact that this bag lives inside a tree decomposition, then the neighbors of this bag share some vertices with it, and that actually defines a supergraph of this one called the torso, in which if you share, these vertices are shared with this other bag, then they must form a clique in the torso. So you have to add all of those edges into there. So there's two graphs, the bigger one with more edges, the smaller one, fewer edges. They both have the same set of vertices. Okay, and the important thing to note then is if I would take a walk around in this tree, you imagine that as is walking around in the graph, the underlying graph. Well, to walk from this bag to this bag, I must pass through a vertex in this clique. So things are separated by these cliques. And so if you imagine I want to talk to you about some path in this tree, one way I could explain the path to you is you say, start at the root, then go through this clique. Okay, now you know which thing you're in. Now from here, go through this clique. And from here, go through this clique. It's a way to describe the path in the tree. There's a little issue, for instance, if I tell you to go through this clique, which way do you go? Don't worry about that. The way we deal with it is we just treat everything, this and this, as all one graph. It just has to happens to have more components. Okay. That's all I'm going to say about tree decompositions, unless somebody wants to ask me about them. Okay, so now we get to this horrible definition, which unfortunately is sort of the way you have to start the paper. So this is called a mixed labeling scheme, but hopefully now there's some motivation for why it has all of these parts. So it's a generalization of adjacency labeling. So there's an adjacency tester just like before. There's something else called an identity tester. It takes 3 arguments, each of which are strings, and says yes or no. There's 2 graphs involved. Bigger graph with more edges, and then one with fewer edges, but they have the same set of vertices. You can imagine where those are coming from. And when you label this graph, the vertices of the, well, actually what you label is 2 things. All the vertices of the graph and the cliques in the bigger graph.
All cliques.
All cliques. No reason not to. Okay, so that's the labeling has a larger set to it. As before, if you give me the labels of 2 vertices, the adjacency tester is supposed to tell you if the edge is there. There's an additional part which assigns for every clique and every vertex of that clique a local identifier for that vertex inside that clique. So if you imagine your graph only has small cliques, then the local identifier of a vertex that belongs to that clique should be much smaller than its description in the whole graph, right? That's the idea. And then finally, we come back to what was this identity tester? Well, it's supposed to take 3 arguments. One of them is a label of a clique. The other one is the local identifier of a vertex in the clique. And the third argument is the label of some vertex in your graph. And it's supposed to tell you if this vertex u inside this clique is actually the same as this vertex v. Okay? So it allows you to do identity testing in a really complicated way. But notice that you never explicitly have the label of u here. You can still test if u and v are the same vertex, but you never explicitly have the label of u. Yeah?
Something like that. You require that something happens if like u is not in k or v is not
So
in k.
there's no, so that this thing is only defined for u's that are in k and v's that are in the graph. Okay. So no, it will only be used appropriately. Okay. All right, so let's look at a very small example to see how we could use this thing. So here's the smallest example, non-trivial example I can think of. It's a tree decomposition with 3 bags, and we'll call those graphs G1, G2, and G3. And then the first thing to notice is it's always problematic that there's vertices that appear in more than one bag because they can't get more than one label. So each vertex that appears will sort of belong to the graph associated with the highest bag that it appears in. In here, they're just kind of, they don't get any labeling from here or anything. We just kind of gray them out for a moment. All right. So, here's 3 prototypical vertices. One is in that top graph, one here, and one here. So let's start with the simplest one in the top graph. What should the label look like? Well, if a vertex is in the top graph, we're assuming somehow that this bag can be labeled as one of these mixed labelings. So that vertex just gets its label in the top bag. So it's just for that subgraph. And that's true even for these vertices here, which look kind of special because they appear in lower bags. They get assigned their label just in the top bag. In a vertex here in a non-top bag, they get more than that. They get a part of the label which tells you how to get from the root to this bag. And the way you get from the root to this bag is you pass through this clique K that appears in this big graph at the root into this thing. So you get a label for that clique from the top graph. Then you get the label of this vertex inside this lower graph, which does not include these shared vertices. And then you get something that I'll call alpha, which alpha stands for adjacency list. I'll get to that in a second. For this V2, it's actually an empty list. V3 is a bit more interesting. So same story. How do I get to this bag that V3 first appears in? Well, I have to pass through the clique K prime. So you get the label for K prime, the label for V3 in this bag, and the adjacency list for V3. And what is the adjacency list for V3? Well, this is supposed to tell you which vertices of this clique V3 is adjacent to. But of course, it doesn't explicitly store the labels of those vertices. That would be too long. It just stores the local identifiers of those vertices inside that clique. Those are supposed to be short. All right, so that's what the labels look like. Let's see if this is enough to do adjacency testing. Let's see what happens if I look at the labels of these two vertices, V2 and V3. Well, label for V2 says if you want to get to the graph where V2 first appears, you start at the root and pass through this clique K. If you want to get to V3, you start at the root and pass through this clique K prime. K and K prime are not the same clique because they have different labels, and so you realize V2 and V3 cannot be adjacent. The answer is no, right away. Let's look at V1 and V3. Well, V1 has one of these really short labels. It has only one part. That means that V1 first appeared in this graph up top. To get to V3, well, you have to start in the graph up top, but then you pass through this clique and end up down here. And if you're not used to this, you'd think, oh, good, now I know that those two are not adjacent because V is up in this graph and V3 is down in this graph. But that doesn't mean they're not adjacent. What you have to do next, V3 is adjacent to some vertices in this graph up here. In fact, it's adjacent to these two vertices. But it has explicitly kept a list of those vertices that it's adjacent to. So I'm supposed to answer 0, but the way you get to that answer is you first ask this question. Look at the clique K prime, look at the local identifier of this vertex that I'm adjacent to in K prime. Is that equal to V1? And do I have the information I need for that? Yes, this identity testing function needs the clique, it needs the local identifier of the vertex in the clique, and it needs the label of the vertex that I want to know if it's equal to. So I have exactly what I need to know if it's that. And so to deduce that V3 and V1 are not adjacent, you have to run through this list, checking that each one of these is not equal to this vertex V1 up top. If you get through the whole list and you didn't find it, you know that they're not adjacent. Okay? And then another example like that, where the answer is yes, you get the label for W, label for V3, you realize W is up top, V3 is below, and you ask the question, here's the clique, here's the local identifier for the vertex in the clique, here's the label for that vertex, are those the same vertex? And the answer ends up being yes. Okay. All right, is that clear? So this is why we need all of those pieces from the mixed labeling. Okay.
Here's a question.
Yes? Pardon?
If you want to test like the adjacency between W and W prime, like
W and W prime are both in the graph G1. We have label of W, we have label of W prime. We just use the adjacency tester inside that graph. And we know they're both in G1 because their labels are both short like this. Good. Oh, actually, that's just the example. If there's a fourth vertex and you realize, oh, they both are in this same graph because they both pass through the same clique, then you use the adjacency tester for this graph down here. Okay. Well, that's all awesome. Let's look at the lengths of the labels, because we haven't done that yet. Well, let's say the number of vertices up here is n1, number of vertices down here is n2, not counting the shared vertices, and n3, not counting the shared vertices. Well, the labels up top they're just one labeling local to this graph. They should have length approximately log of n1 in a lower order term. But the labels here, for example, well, what was the label for V2? It was the label of this clique and the label of V2 down below. That's sort of two parts. And if I don't do anything special, that would mean something like log of n1 plus log of n2. And same thing over here, log of n1 plus log of n3 for vertices down here. And that's not good, because you could imagine all three of these have size n over 3, then the length of this label is something like 2 times log n over 3, which is just about 2 log n. Okay. That's no good. But we've seen this situation before, where a vertex has a 2-part label, which tells you, the first part tells you how to get to the vertex, and then the other part is the actual label inside the location of that vertex. So this is just the same definition as before, but now we have to talk about weights. So a weighted mixed labeling scheme just assigns weights to the vertices, and now it imposes restrictions on the lengths of the labels. So the length of a label for a vertex should be log of the total weight of the graph divided by the weight of the vertex, which is plus some extra overhead, which is just log of the total weight minus log of the weight of the vertex, still plus that overhead. The length of one of these local identifiers, the one that tells you the name of the vertex inside this clique, that should just be a very small function. And then the length of a label for a clique looks a lot like this, except you take, the minimum weight of any vertex in that clique. That's the part that gets subtracted. And so notice on each of these, there's kind of extra G1 term up there. There's a G2 term here, and then there's an extra G3 term there. If all of those are little o of log n, then you say that this scheme is efficient. And so, for example, if I had such an efficient scheme here, meaning that these wavy, almost equal things ignore little o of log n terms, then you get that this works perfectly, because so the weight that I will assign to normal vertices, ones which are not part of either of these cliques, is just 1. But the weight of a vertex, let's say in this clique, will just be the number of vertices down here. Weight of the vertex in this clique will be the number of vertices down here. And now if you look at the length of the clique label plus the length of the label down here, that's just log n. Okay, great. So we can label graphs with tree decompositions with 3 nodes. That's progress. But wait a minute, maybe this solves everything. I mean, 3 nodes. Okay, maybe 3 is special, but what about 1 root and several children? Well, every tree decomposition really is, the tree has 1 root and several children. What are the children? The children are tree decompositions that we could just recurse on. And if you think about this for a little bit, you get really excited and realize, wow, I mean, we found a way to make it so that the sum of this label length plus the label you got here was log n. But actually, if you work through what happens if you just use induction down here, you get really excited and you realize, actually, there's a telescoping series that happens. You get, this minus the weight here, oh, wait, plus something, minus something, and it really works out in telescopes wonderfully. So you get really excited and say, look, here's how I do it. Give me the Robertson-Seymour tree decomposition. With a bit of work, I can adjust the existing schemes for adjacency labeling to do this weighted mixed adjacency labeling inside each bag. And you say, great. So I'll just treat this tree decomposition as having two layers. There's the root layer. There's a subgraph here, a subgraph here, and a subgraph here. Recurse on each one, because they have adjacency labeling schemes by induction, recursion, I don't know. And then this has it by assumption. And you're really happy until you realize, no, it doesn't work. But not for a deep reason. It's just that you forgot something, and it's not such a big deal. What you forgot is that the label for a clique has this length that you like, log of n, or log of the total weight, minus the log of the lightest vertex in the clique, plus another little thing, G3 of n. And you thought that was okay because it was a little o of log n, but that means I get that plus G3 of n here, and then when I recurse, I get the plus G3 of n here, and then again here. But what you can deduce with no more ideas than that is that if you have a bound on the height of the tree, then you get a labeling scheme which is log n plus the height of the tree times G3 of n plus some little o of log n. So it comes close. You just need tree decompositions of small height. Okay? Good? Objections? Complaints? No? All right. Okay. How do you get tree decompositions of small height? Well, one way to do it is to make sure that each time you go from one node to its child, the total number of vertices decreases by a huge amount. By, let's say a factor of b is what I will aim for. So I'll select a bunch of nodes in my tree decomposition, and the criteria for selecting them is I just look at, for instance, the root node here, what's the total number of vertices in all the bags rooted in subtrees of that node? Well, that's n, and that's bigger than n over b, so I better select the root node, and then I do the same things for the children and so on. And so you get something like this. These are the selected nodes up here in the purple thing up top, and then there's these subgraphs that are hanging off. Each of these subgraphs has at most n over b vertices in it, and up top, I don't know, it could be close to n vertices. I don't have much control over that. I also don't know that the height of the thing up top is particularly small. What I do know is that if I were to just contract these things up top, just treat them as their own nodes, supernodes in the tree, then I do get a tree of small height. In fact, I get a tree of height log base b of n. Good. And we end up having to do this for an enormous value of b. So b is not like 2 or 4 or 6. It's something like 2 to the log n to the 3/4, but that's a little o of log n. And when you do that, you look at what does this turn into. That says that the height becomes something like log n to the 1/4. Why those numbers? Just because what we inherit for this labeling schemes for the individual bags has a square root log n in it. And we have to fight with that. But that would be true if no matter what the labeling schemes were in those bags, as long as it was a little o of log n, we would still get the result we want. Okay. The only piece missing now is to say, well, what do I do with these huge bags that I created here? The height for this whole tree, if I can deal with these bags, I'm happy because I already argued that it's just the height of the tree is the only thing you lose from, and we made that small enough. Okay, how do you do that? Well, what's special about this tree? Well, we selected a node to be in, let's say, the top skinny thing up here. We selected it because the number of vertices in the whole subtree was bigger than n over b. So if you think about that for a little bit, and you think about considering the tree layer by layer, what you realize is that in each layer, you could only have selected b vertices. In this case, it looks like b equals 2. So that's a skinny subtree. And these are really unusual trees, right? Like, these are trees with only a constant number of vertices in each layer. It may be long, but that makes them look more like paths than trees. And so, well, first thing we do is, again, we have this issue that there's still things that appear in many places. We associate each one with the first place that it appears, the topmost place, and we kind of forget about it in the rest. And then we just treat this thing as a sequence. It's like a path decomposition of this graph now. So sequence of graphs. Good. All right. Inside of each of these things, we can come up with a mixed labeling scheme for the graph inside each of these boxes. That doesn't solve everything because, you know, there's a vertex down here that could be adjacent down here, that could be adjacent to a vertex up here. We still have to deal with that. How do we deal with that? We put a binary tree on top of this thing, and we look at these special vertices that appear in more than one of these boxes. Like, for instance, this set of vertices appears in those two boxes. And, well, those boxes are now leaves of a binary tree, so we associate those vertices with the lowest common ancestor of those leaves. And we do that for everybody. This thing appears all over the place, so it gets stuck up at the root. This one appears only in two boxes, but that happens to span the root, so it goes up there, and so on for the rest of them. Okay? Good. All right. And now let me tell you what the labels look like. So once you have a binary tree, super common trick is to say, you know, from a vertex, the edge leading to the left child, you label with a 0, to the right child, you label with a 1. And if I want to give you the label for a vertex V, let's say that is in this second box, I give you the directions on how to get to that box in the tree. Follow the 0 edge, followed by the 1 edge. Then I give you the label for that vertex for the graph that is induced by this box. And then I give you another one of these things that looks like an adjacency list, which is supposed to tell you the vertices that V is adjacent to, which are not inside this graph. What are those vertices that V is adjacent to that are not inside this graph? Well, there's a small number of them, and they come from this clique that's shared with something that came before. All right, so maybe then it's worth looking at one of those vertices, the special vertices, the ones that show up in the tree, to see what we should give their label. Well, it looks just like the other one. Directions on how to get to that node, the leaf of the tree that contains the vertex, the label of the vertex inside this graph, the adjacency list for other stuff that it's adjacent to that came before, but there's nothing that's empty. But this vertex now appears up in the tree, and it appears up in the tree, so we want to describe where it shows up in this tree. And the way we do that is, well, look at where this vertex, let's take W from this clique, it shows up at the root. We just say what the depth is of that node that it appears at, 0 in this case. And we give it, there's a bunch of nodes that appear at the root, and we just give a unique identifier among the nodes that appear at the root. There's a bunch of nodes that appear at the root, but it's bounded by something. What's it bounded by? Well, there's at most B things in each set. You can work out that actually it's B times the size of the largest clique. It's the number of nodes that can appear anywhere. So this is like log of B, not log of N. This is like log N because it's just describing a height in a tree whose height is log N. And now I can tell you what the adjacency list for this vertex V looks like. Well, V is adjacent to this vertex W, and so what V remembers is these two values for W. Depth in the tree and the color, the unique identifier in there. And then if I want to do adjacency testing, let's say, I'll just do it quickly. If I want to do V and W, well, I look at the first parts of their labels. I realize that they go to different locations, different bags. And actually, by looking at them, I can realize that actually W showed up first, and then V came along later. So the only way that these two could be adjacent is if W shows up in this adjacency list here. All right, so I can compare these things and these things, and you might say, oh, well, just check if this pair is equal to this pair, and you're done. That's not quite true. It's true in this example. What you have to check first is that when you look at, it's necessary that this pair is equal to this pair for this vertex to be W. But another thing which is necessary is you have to look at this thing that describes a path in the tree. You have to look at the first D steps of that and look at the first D steps of this one and make sure that they didn't diverge before. Because if that happens, then you could be talking, this one may be referring to a vertex in this bag, but the other one's referring to a vertex in some other bag. That's all you have to do. Okay? And that's how you do skinny subtrees. And again, as long as you can do the individual bags, then there's the extra cost is just this, basically this log P. Okay, good. And then the label length you can work out is, one thing to be careful of, this tree up here, it's not a perfectly balanced binary tree. Rather, it's what did I call them? Weighted label of, it's weighted so that the length of the path to one of these nodes is log n minus log the number of vertices in there. That's the trick that we saw at the very, very beginning. Okay, that's all the big ideas. And then here's the proof of the main theorem. If you have a graph class, and every graph in that class has a tree decomposition whose torsos are in a class that has efficient mixed labeling scheme, then your class has an efficient mixed labeling scheme. The proof is take the tree decomposition, turn it into a decomposition of height log base B of n, where each torso has a B-skinny tree decomposition. Apply the previous two results to those things. Now is the time for questions. Okay, good. And the only thing that I didn't talk about is, well, the torsos themselves. You get this tree decomposition from Roberts and Seymour. There's these torsos. We've assumed the whole time that these things have these weighted mixed labeling schemes that are efficient. Turns out that that's the case. And to get that, you don't need any really new ideas that weren't already present in the previous paper, the one that did planar graphs, that did product structure. And that all goes back to the fact that actually the way that that thing worked at a very high level of detail, the crux of it is the label for a vertex is described as a path in a tree, and mostly. And if two vertices are adjacent, then one of those paths is a prefix of the other path. And if you think about what that means for a clique, that means that there's the label for all the vertices in a clique is contained in one path in the tree. So you can read off the label of the clique. It was somehow already present as part of the solution to this other problem. Okay, so summary, we have log n plus little o of log n bit adjacency labeling scheme for H minor free graphs. These are the pieces that you've used to get that scheme. The proof is constructive, and there's a polynomial time algorithm if you believe that there's a polynomial time algorithm for the Robertson-Seymour decomposition of H minor free graph. I mean, I guess that's true in some technical sense, but I don't know of anybody who has implemented it.
But I think we are using the stronger version by Zdenek and Thomas, and I don't think they have that version with polynomial bounds in the product structure results.
Yeah,
So I'm not sure.
we have an email from Zdenek that says there is a polynomial time algorithm.
Oh, okay.
When we did our due diligence at some point for the previous paper.
Oh, you're talking about the algorithm. Sorry, I
Yeah.
take it back. I thought you meant
Oh, yeah,
the
yeah,
bounds,
no, no.
the polynomial bounds
No.
from
Yeah, no, the polynomial inside.
Severin.
Yeah.
Okay, yeah.
No.
Okay, this polynomial time algorithm. Okay,
Yeah.
sorry.
And the adjacency testing procedure, this function that looks at two labels and decides if they're adjacent, it runs in something like log n to the 1/4 time. That's not, don't quote me on this, but it's also not important. What would be exciting is if you could make it run in constant time, because for planar graphs, you can actually make this run in constant time on a computer that has log n bit words and can do reasonable operations on those words. So
Wait, but what is the size of the input to that procedure?
the size of the input is something of size log n, which fits in one word of a computer.
This is, okay, do you have time to read it?
Well, your computer is strong enough to read log n bits at a time.
Okay.
And it's strong enough to even add two log n bit integers together, or
Okay, I see.
yeah, ask for the number of leading zeros and these kinds of little things. But like it's a real computer. Okay, and that's it. Thank you.